Hey kids, yeah, the name's Floyd. I'm Frank's cousin, polar bear from North Pole. No Santa, cool guy. Uh, hey, my uncle Don, you guys know him as Mr. Krolak. Uh, he asked me to, since I'm in town enjoying the nice warm weather you got here, you like my shirt. He asked me to talk to you tonight about Pearson's R correlation coefficient. Uh, lot of words. Pearson's R correlation coefficient. We call it the correlation coefficient where I'm from. Anyways, uh, let's talk about what this thing is. Hey, you can kind of think of the correlation coefficient as like a rating system. It tells you how good your line of best fit is. It tells us how reliable the line is, how well it fits the data. The official word, it's called the Pearson product moment correlation coefficient. What do you think of that? A lot of words. Really, just think about it. It's a rating system. How well does your line of best fit match the data? Okay. All right. So the way that the line of best fit is calculated is known as using a method called least squares regression. All right, well, least squares regression, that's another mouthful. So I'm going to show you a little applet here that demonstrates exactly what that is. Okay, what this method does is it takes the square of the vertical distance between the line and each data point, and it tries to minimize it. So if you look at this little drawing here, okay, let's say we take this point B. Okay, the distance to that line is 2.83. So when I square it, I get a square that has an area 2.83. Okay, you look at C. C is a little bit farther from that line. And so if I square that, that square it's got a larger area, right? Okay, so what we're trying to do is we're trying to find a line here that when we add up these squares, we get the smallest value possible. That's what's called least squares. Least, we're trying to make that the least area possible and add all those up. Okay, now this point G you learned about in the last lesson. Okay, that's the mean. That's the mean of the x coordinates, the mean of the y coordinates. Those in the know call it the centroid of points. And your line of least regression or line of linear regression is going to pass through the centroid of points, right? All right. So let's activate this thing and take a look at how it works. You guys want to bring that over here? All right, thanks. Okay. So you'll notice that I can drag these points here. And as I drag these points, those squares get bigger and smaller depending on where I put the line. So the sum of the squares right here is 1851, 18.51. All right, we want to make that as small as possible. Okay, so first thing I'm going to do is I'm going to make this line go through the centroid. So I'm going to have it show me where the centroid is right there. All right, so I'm going to make sure my line goes through that centroid. Okay, now I'm just going to adjust the y-intercept until I can get the sum of all these squares, these 5 squares, as small as possible. Okay, so getting smaller, small, and I could keep doing this. Well, to save us some time here, I'm gonna click here. It's gonna show me the least squares regression line. Oh, that was pretty darn close. Tell you, Floydo's still got the touch. All right, so if you see, notice if I put it right there, it's minimized uh, the sum of these squares. So that's what the least squares regression line is doing. So when you're doing this on Desmos or on a calculator, inside that calculator, this is what's going on. All right? Okay. Let's go back to our notes here. All right. Now, yesterday when you were doing, or previous lesson, when you did the line of best fit on Desmos, you got the Pearson R right there. Okay, and that's telling you how well your data fits the line of best fit. All right, so when you get that data point, or when you get that number, that tells you the strength of the correlation. That's the R number, the Pearson correlation coefficient. All right, now it can fall into four categories. It can, if it's between 0.7 and 1, that means it's a strong positive correlation. Now remember, positive correlation means as the x or the independent variable is increasing, the dependent variable is increasing as well. A perfect positive correlation would be 1. All right, if it's between 3/10 and 7/10, then we say it's got a weak to moderate positive correlation. If it's 0, notice there's no 0 on this chart here. 0 means it has no correlation. All right, now when we go to negative, so there's our, that would cover our 0 in there, no correlation. All right, now if we start going in the negative direction, we go negative 0.7 and negative 0.3, we get a weak or negative correlation. So remember, a negative correlation means if the independent variable is increasing, the dependent variable, the y, is going to be decreasing. So as x increases, the y value, which is your dependent, is going to decrease. When it's a positive correlation, as x goes up, y goes up as well. Okay? A perfect negative correlation would be -1. So if we look at these examples here, we could see that this one's got a pretty strong positive linear correlation. Its Pearson R is 0.8. Right? Here, so you can see as x gets bigger, the y coordinate gets bigger. Over here, we got a perfect negative correlation. So as x is getting bigger, the y value is getting smaller. Right below it, we got a perfect positive correlation. And next to it, we've got a moderate, because if you look at the Pearson number, it's only negative 0.5. So we've got a moderate negative correlation. All righty. So that's that size of that correlation is dependent on the size of R. The closer R is to 1, the closer the fit. The closer R is to -1, the closer the fit. It's just a negative correlation. As x is getting bigger, y is getting smaller. All righty. Now, calculating the Pearson R correlation coefficient. Well, the formula here is pretty crazy. Uh, so we're always using a calculator to do this. It gets just too tedious to do it by hand, and you probably end up making a mistake. So you can do it on TI-84. You can do it on Desmos. I'll show you how to do it on Desmos here real quick. Well, it comes up automatically when you do your linear correlation. Okay, so here's two tables of data. We're going to plug these into Desmos as tables, and then we're going to calculate their correlation coefficients. All right, so fellas, you want to open up that Desmos file for me? All right, so I went ahead and entered that data and made it into a table. Then to get the line of best fit or the linear regression, what you do is you just type in Y1, so it's real simple. Let's say I just got rid of this here. Okay, I go Y1, and then I put in the tilde symbol. So on my keyboard here, it's pointing at it. You see it down here by the parentheses. And then I go MX1 plus B. And there's my stats and my line in red for that first table of data. Okay, and then I just added a second table of data, and I did the same thing. Okay, gives me my slope, my y-intercept, slope, y-intercept. You can see we got a positive correlation for the first table and a negative correlation for the second table. So that's where I got that data that I pasted in there. Okay, boys, you can take that away. Oh, what the heck is that? Okay. Oh, what the heck? All right, here we go. Okay, so there's our data. Okay, and then here's our correlation. So we've got a pretty strong positive correlation going on there. And then here we got a pretty strong negative correlation. All right. So that's pretty straightforward, and that's just from using Desmos and a table of data. All right, so what we're going to figure out now is this concept, or we're going to talk about is this concept of being statistically significant. All right, so think of it this way. If you look at it, think of an example. What would you think would be more useful for making a prediction? If you had a set of 5 data points and it had a correlation coefficient of 0.9. All right, so let's highlight that. I got 5 data points, correlation coefficient 0.9. That's pretty strong positive correlation. All right, now, would that be more useful for making predictions than if you had 50 data points? So a lot more data points, but a lower correlation coefficient. Which one would be more useful for making a prediction? All right, so the way that we determine that is this concept of statistically significant. So what you're looking at over here is a table of what we call critical values. And what we do is we take our R value and we compare it to the R to a critical value that is in these chart here. Your critical values are these numbers in blue. It's probably kind of hard to see. There's a clear chart in your cognitive textbook, Mr. Krolak tells me. All right. So what we got up here is we got three columns. Okay, the first column right here, that has to do with the number of data points you're using. And the way the table is set up is the row that you're going to use is the number of data points minus 2. Okay, so for our first setup here in yellow, we had 5 data points. Okay, 5 data points, take away 2. Guys, do that in yellow so colors match. All right, that's right there. All right. So I'm going to highlight that column or that row. Okay, our other set was 50 data points. Okay, so I'm going to go to where's 50? 50 take away 2, that's 48. So I'm going to color code that in green. All right. Now above that, we've got these two columns. One is ooh, that's too dark. Okay, one is 0.05 and one is 0.01. All right. What those are called are your confidence levels. Okay. So if we're going to use the 0.05 column, here's what that means. Okay. If a column is 0.05, it contains the values that indicate whether a correlation has a 5% chance of occurring randomly or by chance. So in other words, there's a 95% confidence that the correlation is statistically significant. That means it occurred not because of chance. So you're 95% sure that what you're looking at in your best fit line did not occur by chance. Now you can even tighten that up better. Okay, you could go to a confidence level of 0.01. Okay, so what that means is 0.01 column gives the critical values that help us determine we can be 99% confident in the significance of our correlation. Right? So there's a 99% chance that the correlation that we're seeing didn't happen randomly. It didn't happen by chance. There's only a 1% chance that it did happen randomly. So most likely what we're looking at did not happen randomly, and therefore we can say it's statistically significant. All right. So that's our first step. You decide which value of confidence you want to have for your particular set of data. You want to be 95% sure, you want to be 99% sure. Okay. Now, what you do is you find the degrees of freedom, which is the number of data points, take away 2. Right? So that was our 50 take away 2, 48, and our 5 take away 2, 3. All right. Let's say that we want to be 95% confident. All right. So we're going to take our R value and take its absolute value and see if it is greater than the critical value for our degrees of freedom. If it is, then we know that what we're looking at is not due to chance, meaning it's statistically significant. Didn't happen randomly. All right. So for our white or our yellow data here, it was 0.9. So to test that, hold on. All right, sorry about that. Ooh. All right, okay, here we go. All right, so let's see. R was what did we say? It was zero point 0.9, right? Okay, so the absolute value of zero point 0.9 is greater than. Now I go over here. We're using the 95% confidence column. That's 0.878. Yep, zero point 0.9 is larger. So it is okay to make predictions using that data. Okay, so it's okay to use that. Looks like I froze in the picture, fellas. You see, we can get someone on tech on that. Okay. So even though we only got 5 data points, that fits it. It satisfies the critical value. So it is okay. It is statistically significant. It reaches that threshold. This is fine for making decisions. All right, now let's take a look at our 50 data point one. All right. Well, to be statistically significant, our R value for only has to be greater than 0.279. That ain't much. Okay. So ours was 0.75. Plenty. Okay. Way bigger than its minimum critical value. So this would also be okay. You could say it's statistically significant that what I'm noticing in this line of best fit data, it's okay for me to make predictions based on it because it satisfies critical value. Okay. All right. So here's an example. The other day we were doing a prediction between how far you could jump horizontally compared to vertically. All right. Here was the graph that we got, and here's the data that we got. All right. our Pearson number was 0.822. Okay, we had 15 students, so our degrees of freedom is going to be 15 take away 2 or 13. All right, we're going to determine that we want to have a 95% confidence level that the correlation is statistically significant. So we go to row 13. We go to the 95% column, and our value has to be greater than 0.514, and the and that's the absolute value of it. Okay, well, this doesn't really matter because it's positive, but we had an R value of 0.88. That's bigger than 0.514. We can be 95% sure that what we're seeing here is a correlation that didn't happen by chance. So it's a pretty good idea that we're looking at. There's a positive correlation between how far you can jump horizontally and where you can go vertically. All right. Okay, here's another one. Let's say you're conducting an experiment to determine if there's a relationship between the number of police cars driving through an intersection and the number of vehicles passing through the intersection illegally. All right. You collect data for 25 days and you end up with a data set of 25 and you get an R value when you plug it in and you take your line of best fit, you get an R value of 0.685 negative. All right. Our degrees of freedom on this are going to be 25 take away 2, 23. And let's say that for the sake of our research, we've decided we want to be 95% confident that the correlation is statistically significant. That means it didn't happen by accident. It wasn't just a random occurrence that what I'm seeing happened. I'm 95% sure. All right, so here we go. Here's my 95% confidence column. Here's my degrees of freedom. And my critical value is 0.396. And I want to be sure that the absolute value is greater than that. And if it is, then the correlation that I'm observing is I have a 95% confidence that what I'm observing didn't occur by chance. And yep, that works. So if I was writing a report on this and someone says, well, how do I know that's just not random? I can say, well, based on the critical value test, I'm 95% sure that what I'm viewing here did not happen by accident or by chance. And we can justify then our statements about the correlation. So if you notice, down here under my conclusion, our absolute value was greater than this is our critical value. All right, then the correlation that we're seeing is probably not due to chance, meaning it is statistically significant. You can say that you are 95% confident there is a statistically significant negative relationship between the number of police cars driving through an intersection and the number of vehicles passing through that intersection illegally. Which makes sense. The more police cars you see, chances are you're not going to run a red light or go through that intersection illegally because you probably know, well, if I do that, I'm going to get busted. Right? Yeah, it doesn't take very smart bear to understand that. All right, fellas and ladies, excuse me. All right, let's take a little couple examples here. Uh, it says match the scatter plots with the following correlation coefficients. So we got a negative 0.8 and a negative 0.5. So our negative correlations are going to be, looks like figure 2 and figure 3. Let's shrink that up. Yeah. Okay, the one that's tighter to a line, that's going to have your higher correlation coefficient. So I think a good guess would be this would be 0.181. This is negative, but it's not as tight. Okay, the distances that these points are from this line are going to be bigger, so that when we square them, we're going to get a larger area. Remember that least squares regression demonstration I did earlier. So I'd say that this one here is your negative 0.5. Alrighty. Then we got an R of 0.55, R of 0.96. Well, that's pretty good fit up there. That's got to be your 0.56 or your 0.96. And I'd say down here is your 0.55. All right. finally, the last one is just Desmo's question, guys. So it's got Alejandro is exploring the connection between the heights and centimeters of his berry bushes and the kilograms of berries he harvests from each. Data collected is shown in the table below. All right, find the correlation coefficient. So these are the heights, and this is the number of kilogram berries. So you go to Desmos. Mr. Crow put links to these in your Google Classroom. I'm just going to show you what the results are. There's our table. Here's our line of best fit. And if we're looking at this, wow, pretty good correlation, 0.99. We got a pretty positive correlation going that as the tree gets higher, the amount of the kilogram of berries increases. Oh, it gotta make sense. All right. Okay, guys, that's it for today. My name's Floyd. I'm a cousin of Frank. Frank and I are hanging out down here in that nice warm Arizona weather with our Uncle Don, Mr. Krolak, to you guys. So I appreciate them letting us come on here and help you guys out. And take care. And I'll see you next time.